Hi there, I'm Micaela Kaplan, the ML Evangelist at HumanSignal, and this is In the Loop, the series where we help you stay in the loop with all things data science and AI. This week on In the Loop, we're going to start a series of videos on annotator agreement, what it is, why it matters, and how we can use it to get high-quality data for training or evaluating our models. Let's get started. Say you're working on a project, perhaps evaluating the output of an LLM. For the sake of efficiency, bias reduction, and completeness, you'll want multiple people working on this project simultaneously. In order to get an evaluation that we can trust, we need to know that the responses that we get are all high quality and consistent. How can we ensure that our annotators are providing the correct label and are consistent among themselves, even when there isn't always an obvious right answer? After all, humans are free-thinking and can make their own judgment calls. Especially for ambiguous or subjective cases, like emotion detection, it can be hard to ensure that your annotators are on the same page, thus jeopardizing the quality of your data. To solve this problem, we can implement overlap into our projects. Overlap defines how many annotations you want on each task and for what percentage of the tasks you want a given number of annotations. By leveraging an overlap, we can evaluate how different annotators would annotate the same sample, giving us a proxy metric for quality as well as a deeper understanding of how each of our annotators is performing. For example, in the LLM evaluation case, you might want to have at least 2 annotators on 20% of your tasks. And only overlapping 20% of the tasks, we can optimize for efficiency by not making all the annotators annotate every sample, and still get enough data to understand the quality of our annotations and whether or not the annotators are on the same page. In a relatively straightforward task, where the questions are relatively unambiguous, a 20% overlap is more than enough to balance quality with efficiency. If we were working on something more subjective, say emotion detection, we might want a higher level of overlap on more of the tasks to make sure that our data is reliable. If we have multiple people annotating a single task, we need a way to measure how similar or different these annotations are. This measure, known as agreement, is an industry-standard proxy for the quality and correctness of the annotations. There are a variety of inter-annotator agreement metrics, sometimes called inter-rater reliability metrics, we can use to get this measurement. Today, we'll focus on a few basic metrics, but in the upcoming videos, we'll deep dive into some more statistical measures. One simple annotator agreement metric is a simple pairwise comparison. In this approach, we take a look at each answer as compared to every other answer in pairs and average their scores. This approach gives us some insight into the quality of the data itself, but more insight into the agreement of our raters. In fact, using pairwise agreement, we can build a table that maps how frequently each annotator agrees with each other annotator, which allows us to identify our strongest annotators, those who agree with others the most, and our weakest annotators, those who disagree with others the most. These weak annotators may require more training. Let's look at the LLM quality example. Let's say that you have 4 annotators, 1, 2, 3, and 4, and that you've asked them to pick between 3 possible LLM responses, A, B, and C. They annotate as shown on the screen. We'll compare each annotator to each other annotator as follows. First, we'll compare annotators 1 and 2. They disagree, so they get an agreement score of 0. Then we compare 1 and 3, who agree, so they get a score of 1. Next, we compare 1 and 4, who disagree, so they get a 0. We then move on to 2 and 3. They disagree, so they get a 0. Then we continue with 2 and 4, who also disagree, so they get a 0. And finally, 3 and 4 also disagree, so they get 0. If we average all of these scores together, we get a pairwise agreement of 0.1667. This tells us that the 4 annotators disagreed with each other pretty substantially, and that we need to investigate more on the sample to figure out why it has low agreement. You may need to update the labeling instructions to cover a new edge case or ambiguity, or maybe the discussion leads to a deeper understanding of your class's labels or the task in general. Another type of metric we can calculate is an aggregate metric. In this case, we'd want to compare all of the answers at one time and take a majority rules approach. Let's work through this example together. We'll use the same leveling setup as before, with the 4 annotators selecting from 3 choices as shown. In this case, we counted the number of times each answer appears. A appears twice, B and C each appear once. This gives us an agreement of 50% overall, because 2 annotators selected the majority answer out of 4 total annotations. This doesn't tell us anything about which annotators agreed with which other annotators, but it does give us a good sense of the correct answer to the question, and gives us more confidence in the majority answer, although 50% is still pretty low and may require further investigation. How do we know whether to use pairwise or aggregate agreement? It depends on what you're doing. If you're trying to pick the answer that is most likely to be true, you'll probably be happy with an aggregate agreement, which will give you the most agreed upon answer to use for training or evaluation of your model. If you're trying to see how well your annotators perform, you'll want to use pairwise metrics. This allows you to build a table that compares, on average, how well each annotator agrees with each other annotator, which can help you find your strongest and weakest performers. It can also help you focus on tasks that might be more ambiguous. If the annotators disagree, there's probably something to talk about. Annotator agreement metrics can help us understand how our humans compare to each other. This helps us ensure that we get reliable, high-quality data from our humans that can be used to train or evaluate our models. This week, we covered simple exact match agreement in both pairwise and aggregate forms. These metrics, however, don't account for random chance. Next time, we'll talk about some more statistical metrics that you might use to take this chance into account, such as Cohen's kappa or Krippendorff's alpha. That's all for this week. Thanks for staying in the loop. Looking for more In the Loop? Check out our other videos. Don't forget to like and subscribe to stay in the loop.